like this little parts that you dig inside, like even like what if you put it in your brain and try to reduce it? I'm actually right.
Well, now you don't need to go here. That's also
Okay. Is this mic working? Great. Great. And this is working.
there's a point
Great. Oh yeah. Great.
Okay, so for the final talk of the morning, we'll have Walker tell us about celestial amplitudes as AdS-Witten diagrams and the leading soft algebra.
Hi. So. Great. So ready? Great. So first, I'd like to thank all the organizers again for having this wonderful conference and giving me a good excuse to come to Greece for the first time. Anyway, so today I'll be talking about some recent work with Eduardo Casale and Andrew Strominger, and then briefly a follow-up to appear on the archive with Shruti Narayanan and Andrew Strominger, which we're still working on, but we have some preliminary results to discuss. So as a brief outline of the talk, I begin by talking about some brief motivations for the work in relation to the translations in celestial CFTs, as well as trying to find some relationships between celestial holography and features of AdS-CFT. After that, I'm just going to give a brief background on Yang-Mills and massive scalar theory we consider, as well as Klein space, and then discuss how we construct all plus gluon amplitudes at tree level in a particular background and relate them to contact scalar Witten diagrams. Finally, I'll describe the soft and collinear structure of these amplitudes after adding the background deformation, and finally, possible deformations of the leading soft algebra. So the first motivation is in celestial CFTs that they possess sort of the full symmetry group of flat space scattering, including the Poincare group. So they're invariant both under the Lorentz group that becomes the global conformal transformations of the celestial sphere, but also as translations. And these translations act on conformal primary states, so it's for massless particles, by simply multiplying by a function of z and then shifting the weight up by 1. And these symmetries are rather unfamiliar from the context of lower dimensional CFTs and imply effectively that their correlation functions, these celestial amplitudes, obey a set of new Ward identities. And these Ward identities imply that low point amplitudes of massless particles are generically singular. 2-point functions have to vanish. 3-point functions can be non-vanishing only in Klein space and still have support only where z12 is equal to z23 or z bar 12 is equal to z bar 23, where these are the locations on the celestial torus for the two massless particles. And 4-point functions have support only where the cross ratio is real. And all of these sort of don't match our expectation from a familiar CFT perspective, where we'd expect that there would be, say, a standard 3-point structure that just depend on the difference of the coordinates, but was generically non-singular, and where the 4-point function would be non-singular across the entire, ideally celestial sphere, and would only become infinite when particles would become collinear. Okay, and in particular, some of these divergences may be explained by having a non-compact spectrum for the celestial CFT. And we've done some work that look into, say, expressing the delta of z minus z bar in terms of sum over an infinite number of conformal blocks, and you can make this work out. But the other thing we can try to do is try to get rid of these symmetries. And we can get rid of these symmetries by trying to break some of the symmetries of the celestial CFT in a controlled way, so that we can still see as much of the features of it as we can, such as Lorentz invariance, conformal invariance, say, the OPE, and hopefully some soft theorems, while having a model that is ultimately less singular than the celestial CFTs so far we have seen. Okay, and so we're going to do this ultimately by adding a background and considering scattering in a background that breaks translation invariance but preserves Lorentz invariance. Another motivation is that we'd like to understand any possible connection with other forms of holography, in particular AdS-CFT. And at least perturbatively in AdS-CFT, we can boundary correlation functions perturbatively by summing over Witten diagrams, essentially products of bulk to bulk and bulk to boundary propagators that we integrate over the bulk AdS space. And we know that in flat space, we can foliate flat space with generally constant x squared slices that are geometrically either AdS or ds. And hence we like to perhaps find some way to interpret these celestial amplitudes as perhaps some integral over over some Witten diagram where perhaps we're varying the radius or like the constant curvature on each slice. Okay, and so we're going to sort of do both of these at once, and we're going to work in particular in this particular Yang-Mills theory coupled to a massive scalar. So we have actually just Yang-Mills, we have a massive scalar. We're going to couple them together with a simple interaction as phi trace F plus F plus. Here, F plus is the self-dual component of the field strength, and it couples only to, and so our background field phi will couple only to positive velocity gluons. And in particular, so our strategy is going to give phi a position-dependent background. This will break translation symmetry, but in a controlled way, where the amplitudes will still be relatively simple and allow us to say some things about the resulting amplitudes. Yes. Well, my first thought would be you could just set the background. If we don't care about it solving the equations of motion, you could just set it to be 0 outside of some box, perhaps, or inside some box. Well, that would kill, yeah. Well, probably, yeah. If I suppose I just set phi to somehow be Win to infinity at some finite distance, any kind of solution outside of that might blow up and vanish, but it's not something we thought about so far. So far, we focus on giving phi a background that depends only on x squared, so that it preserves Lorentz invariant. Yeah, I suppose we could either try engineering it to have poles or zeros and some range that would at least give the leading order background might have some cutoff outside of that region, but we have, which could be interesting to consider, but this is not something we thought about yet. Okay. Great. So in particular, amplitudes in this theory have been studied in the past in the context of Higgs and multi-gluon amplitudes. And in particular, for our particular coupling here, where we couple to F plus squared, there are in fact two classes of amplitudes that are particularly simple. There, first of all, are the all plus amplitudes in this background. Now, at zeroth, like if we don't have the scalar, like the all plus amplitude at tree level, without the scalar would vanish. But if I have a single scalar inserted, this amplitude is just instead just the coupling constant that couples the scalar to the background times m to the fourth divided by the Park-Taylor denominator, and then a momentum-conserving delta function, just enforcing that the sum of all the momenta, including the momentum of the background field, or a scalar, is vanishing. And the MHV bar amplitude in this background are also similar, and are effectively just take the form of like a simple MHV bar amplitude without the background, but where we've shifted the momentum-conserving delta function to include the momentum of the scalar. Beyond these amplitudes, you can sort of sew together these amplitudes using MHV rules to build up more complicated amplitudes, but they generically depend more complicated on the field, on the momentum of the scalar. So we're going to focus, in particular in this talk, we're going to focus on the all plus amplitude case as sort of the simplest set of amplitudes we can work on that are closed under the leading collinear and soft limits. So in particular, now that we have our amplitudes, we're going to want them to consider amplitudes of n gluons of positive velocity in a particular background. And we're going to want this background to do a few things. First, we're going to want it to solve a massive wave equation. So that d squared minus m squared phi is equal to 0. We could in general look at a general background, but this seems particularly nice because sometimes we can interpret adding this background field to the action as some type of conformal perturbation theory of the boundary theory. And if we want this background field to somehow appear in the spectrum, we'd want it to solve the equations of motion, presumably. We also want that our background solution is damped for a large space like X, and this is so that some integrals we'll deal with later are convergent, because this will give some exponential damping for large tau, and so that would be just a nice feature of the solution. And finally, we want it to be a function of only x squared. And the reason we want it to be a function of only x squared, although it could, is that because x squared is invariant under Lorentz transformations. If we consider amplitudes scattering in some background, our amplitudes will preserve whatever symmetries the background preserves, and whatever series the wider theories whatever symmetries the wider theory conserves. So if we choose some background that preserves Lorentz invariance, the amplitudes we'll get out of this will also conserve Lorentz invariance. And once we transform to the celestial sphere, we'll transform like correlation functions of n primaries under global conformal transformations. So in particular, the amplitude that's sort of the background field that satisfies all of our requirements is just going to be the sum of the weight 0 massive conformal primary modes, where we sum over both the ingoing and outgoing mode. And this takes a pretty simple form, it's just a number divided by tau of a Bessel function of negative I m tau, where tau is just the square root of negative x squared. Okay. And so now, in particular, given our momentum space amplitudes, including the scalar, we can calculate our background amplitude by just sort of convolving the momentum of the scalar against the momentum space wave function of our background field. Here I haven't described the actual momentum space wave function, but it is particularly simple, and we can do this explicitly. But remember from the beginning, we also want to try to make, and then so once we do that, we're just going to Melton transform the rest of the particles, right? So we're going to take our momentum space amplitude in the background, we're going to Melton transform with respect to the energies of all of the gluons, and that's going to give us our celestial amplitude of n positive. So gluons with some weights delta 1 to delta n, and then whether at epsilon 1 and epsilon n is just whether they're ingoing or outgoing. And here I'm working with color ordered amplitudes, so we've stripped off the color index A, which we can easily restore and will do later. But remember, we also wanted to try to make some contact with Witten diagrams as integrals over particular slices of Klein space. And so we're going to try to evaluate this integral by taking our momentum conserving delta function, which requires in all of our amplitudes here, and expanding it as an integral over Klein space. Where we take an integral, where we see we extend the d4p as just a simple integral, and then performing the Melton transform is simply going to give us integral. We get this sort of simple kinematic prefactor that's just sort of inherited from the momentum space amplitude, and then an integral over d4x with our background field phi b of x, and then a product of j conformal primary wave functions. And these are just the massless scalar conformal primary wave functions with weight delta j minus 1, or where this just comes from multiplying the momentum space amplitude by some factors of omega. Okay. So in particular, we could do this integral directly in Minkowski space, where we would foliate it with slices of Euclidean AdS space in the time-like region, and Lorentzian de Sitter space in the space-like region. But this would rather be a little hard because they're not sort of geometrically the same. So as a sort of computational trick, we're going to work in Klein space instead. So Klein space, as we've seen before, is a 2-2 signature metric. And in particular, if we want to foliate it with sort of AdS slices, we can look at a particular foliation where the metric just takes a simple form of negative d tau squared plus tau squared d squared h in the time-like region, and just a negative of that in the space-like region, where d squared h is the metric on AdS3 mod z on each AdS3 mod z constant x squared slice of Klein space. And so the nice thing here is sort of they're both geometrically AdS3 mod z, and this will simplify some of our integrals later on. Generic null momentum will appear in the bulk topology propagator. Here is just this familiar formula, but now where z and z bar are independent real variables rather than being complex conjugates of one another. And so finally, here we can see sort of the toric Penrose diagram of Klein space. These blue lines are the constant x squared slices of Klein space. And so we're going to do our integral by integrating over these like constant x squared slices in both the time-like and space-like regions, and then integrating over x squared separately. And that integral will cover the entirety of Klein space and will hopefully give us some celestial amplitude that we can then study. Okay. Okay, in particular, we could do this we're also going to use this sort of trick by relating the integral in tau to a sort of contour integral by noting that if we have some analytic function with certain pole configurations, I can take my integral of d4x over Klein space, and I can relate this to an integral where I do a contour integral in tau of d tau tau cubed, and then our f of tau x hat, and then I can integrate over x hat, where x hat is like a unit time-like position, so that x hat squared is always equal to -1. And this contour in tau runs from I infinity down the positive imaginary axis and then along the positive real axis. And the region where tau is real will cover the time-like region of Klein space. The region where tau is imaginary will cover the space-like region of Klein space. And we will get our full integral by doing this sort of a contour integral. And for our amplitudes, a specific choice of I epsilon procedure can be chosen to guarantee that our integrand will satisfy the correct analyticity properties so that we can do this contour rotation. So now let's see what we get. So we're going to take our all plus amplitude, and we're going to plug it into this formula. So we get our simple kinematic prefactor, along with some functions of the weights that just come from the normalization of the conformal primary wave functions. And then we get an integral over x of our background field x times the product of j, I think it was 1 over negative q of zj bar dot x to the delta j minus 1. These just come from our conformal primary wave functions. Now we're going to plug in our formula for the integral over Klein space, and we get this contour integral in tau. Our background field function is evaluated at tau x, and then our product of j conformal primary wave functions evaluated at tau x hat. Okay. So what we can do now is we can take this integral and we can split it into a few separate parts. So first we get the simple kinematic prefactor. So after that, we can pull out a factor of tau to the negative beta from the conformal primary wave functions and integrate over tau. In particular, here we've done that. We've closed our integral over tau around the positive imaginary axis, and that's pulled out a factor of e to the negative 2 pi beta minus 1 from taking the discontinuity across a branch cut. And we see that now we just have this sort of tau integral now just sort of pulls out. We get a nice Melton transform of the background field. And what we're left over with is an integral over the AdS-3 mod z slice of the space of the time-like region of Klein space, where I'm just integrating a product of J bulk to boundary propagators on that slice. And so we can recognize now this amplitude has a few simple parts. The first part we see is we have a simple kinematic prefactor that comes from the coefficient of the momentum space amplitude. We have a simple function of beta that sits in front that is effectively just a Melton transform of the background field. And it really depends only sensitively on the details of the background. And finally, what we're left over with is just the integral over AdS-3, which you can recognize as a scalar contact-Witten diagram of n massless of n scalars of weight delta j minus 1. Okay. Yes?
Sorry, maybe I missed this, but also where does the AdS-3
effectively it comes through tau. Like since effectively I'm integrating over the x squared equals negative tau squared slices and then integrating over tau squared. But I sort of pulled the tau squared dependence out as a prefactor, and so it appears in this like prefactor that depends on beta. It's effectively like the beta is telling me how the different AdS slices are weighted relative to each other. But as a function of the positions, it really appears only as a prefactor. And the functions of the positions of like the z bars is effectively like only in the prefactor and then in this leftover Witten diagram part. Okay, and so in particular, okay, we can study this. You know, we have contact Witten diagrams have been studied extensively for 2 and 3 points. They can be these integrals can be evaluated analytically, and I'll show you the results of that in the next slide. For 4 points, there is no analytic expression for the contact Witten diagram, but there is a special function called the d function that evaluate that. It's turned out, and a lot about this d function is known, such as various formulas at specific weights, various recursion relations when the weights become shifted by integers, and also its full conformal Bach decomposition is known. So in particular, for 3 points, we can take our integrals and we evaluate it explicitly, and we sort of go through this in a paper. We have that our 3-point function now, 3 massless gluons, and we've stripped off the color ordering. We're storing the color ordering. We'll just effectively multiply this by IFABC. And so here we have simple p parts. We have our e to the 2 pi beta minus 1 that comes from just taking the discontinuity across a branch cut, a factor of 1 plus negative 1 to the beta over 2. And this comes because each x hat squared equals negative 1 slice contains 2 point gray patches, and this accounts for the fact that we're integrating over both of them. We have our Melton transform of the background field, and then finally we have a product of just a bunch of gamma functions that comes from integrating over the AdS-3 slice. You can work this out explicitly, and then finally we just have the standard, essentially conformal 3-point structure of z and z bar. And now while this last part looks like it sort of is a correlation function of 3 scalars of weight, delta 1 minus 1, delta 2 minus 1, and delta 3 minus 1, the prefactor 1 over z12, z23, z31 guarantees that this 3-point function transforms correctly for particles of weight delta and spin 1. So now we have our amplitudes, right? We want to look at whether our background has sort of deformed the soft and collinear structure of the amplitudes. And so to do this, we just look at the soft and collinear limits. We know that if I take the first particle soft, going back into our formula for our amplitude here, we can see this is effectively, say then here, gamma of delta 1 minus 1 is going to go to gamma of 0. There's a pole, and we can cancel that pole with a soft factor, and then just pull out a simple factor from the kinematic, from like the sort of prefactor of zi and zi bar. And we see that we basically just see that the limit of epsilon goes to 0. This, taking the soft limit, just reproduces basically exactly the leading soft theorem for a positivistic gluon before the background, which sort of makes sense because our dependence on the background is sort of left over in the lower point amplitude, and so it would make sense that it doesn't affect the soft theorem. Similarly, we can also look at the collinear limit between 2 positivistic gluons, where I just say take z12 to 0 and fix z bar 12, and then Taylor expanding our integrand here, where z1 and z2, for example, go together, and z bar and then expanding in z bar 1 minus z bar 2 gives a simple formula for the operator product expansion. We just have 1 over 2 z12. And I have a beta function of delta 1 plus m minus 1, delta 2 minus 1 over m factorial, and then times z bar 1 to the m, v bar 2 to the m times the lower point amplitude, where I have a single gluon of weight delta 1 plus delta 2 minus 1 evaluated at point z2. And this is, again, the OPE the same as the OPE without the background. It may look a little unfamiliar, but that's because we're working with color ordered amplitudes. Restoring them would just restore a factor of I of ABC here, and then this would just have weight C. And again, this makes sense because our dependence on the background is sort of left over in the lower point function. And so we wouldn't expect to see a variation for the OPE in the leading structure because all our dependence on the background is in the lower point function. It's sort of happening far away from the particles we're taking collinear. Okay. So in our paper, we also described the collinear structure between a positive and negative velocity gluon and a negative velocity gluon, and we sort of describe how they're related to the similar structures before the background. But in the interest of time, I think we're going to work. This sort of contains all the interesting physical aspect. Okay. So in particular, if I look at these diagrams, and initially it looks like the OPE is unchanged, the leading soft theorem is unchanged. So you might think that this doesn't sort of affect the leading soft algebra. And that makes sense, but actually there's some variations we can't really see because we're working only at first order in the background. Generically, if I was going to look at all orders in the background, I could say look at amplitudes where it interacts with the background once, amplitudes where the gluons interact with the background twice, and so on. And so there could be, for example, if there was a perturbation of the OB at linear order in mu, I may not see it here because I always have to leave my background in the lower point amplitude. But the one way we can see that there is perhaps some modification of the algebra is by looking at the gluon, the 2-point gluon correlator. Effectively, an amplitude where in our background, 2 gluons just scatter and interact with the background and scatter into nothing. Okay, so in particular, we're going to investigate this, and then this is going to appear in some follow-up work along with Shruti and Andy, hopefully soon. We're going to take our 3-point function that we computed here, and we're going to look at the amplitude where all 3 particles become soft. And in particular, so taking the sort of simultaneous soft limit of this amplitude, where each one has weight 1 plus epsilon, and then taking the limit and canceling sort of 3 poles, we see this simply, this is just equal to 4 times mu times the structure constant FABC, where I'm now looking at the full amplitude by summing over different color orderings, divided by Z12, Z23, and Z31. Yeah. So mu is just the coefficient of the phi trace F plus squared interaction. Right? It's just all our, and we're working at linear order in mu. So we're looking at amplitudes where there's exactly one scalar interaction with a scalar background. Sorry, what did you say? Mm-hmm. Mm-hmm. Yeah, here we're focusing on, in particular, the all plus amplitudes for simplicity. If we wanted to, for example, we could add like a trace. I think we could add like a trace of BF term to this interaction and then sort of work with sort of a self-dual theory. In particular, we focus mostly on positive velocity gluons because there are some deformations of like the OPEs when there are negative velocity gluons involved. Okay. So in particular, we can see is basically that there's a sort of simultaneous 3 soft current is finite. It gives us this 4 mu FABC divided by Z12, Z23, Z31. And by staring at this function, looking at, say, the collinear limit where Z1 goes to Z2, we see that if I sort of want to interpret these soft currents, say I'm going to call J1A as some operator and look at their OPE, we have the familiar sort of soft algebra like I of AB1, ABC, J1C over Z12. That will come from, as effectively, should be familiar from the soft OPE. We also have a new term with 4I mu delta AB divided by Z12 squared, term proportional to the identity. And this is responsible for the fact that this 3-point function is now non-vanishing. In particular, this term also appears if you're studying Kac-Moody algebras for this current algebra, and it particularly implies that this Kac-Moody algebra now has a non-trivial level of K equals 4I mu. So particular, so from this, we can calculate the endpoint soft current correlator sort of recursively on this by building it up with a soft theorem or by using this form for the OPE. here. And you see it just takes this pretty simple form. We just take negative 4i mu times a trace of these TA1 to TAN, where these sort of generate SUN, and then times the normalization factor, and then just Z12 ZN1 plus dot dot dot. And this dot 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 includes different color orderings, as well as products of, say, disconnected diagrams that are higher order in mu. Number two, okay. And so basically that is, so basically now, so currently we're just working out some more details of this. And we are also currently in some future work and hopefully some work up here. We're going to try to generalize this to consider, say, central, whether this gives a central term to the soft algebra for weights, say 0, -1, -2, or so on. Since there's no particular reason to think that this expression will stop at leading order. And so we're currently working this out now and seeing if there's any other deformations to the subleading soft algebra, as well as understanding sort of what the allowed deformations are. And finally, we can also recognize that these correlation functions, these n currents, look exactly like the correlation functions of n holomorphic currents in a WZW model with level k equals -4i mu. And we are currently also trying to think about whether we can sort of use this to develop some more rigorous correspondence between a WZW model with a particular level, and particularly in the all holomorphic sector, and sort of the soft scattering in this Yang-Mills with a background. So that's basically what I wanted to discuss today. So if anyone has any questions, please feel free to ask. I hope this wasn't too short. I was told this would be a 20-minute long presentation at first. So we'll be leaving good time for questions. Yes, we're currently what we're working on is taking this 3-point amplitude with the background, and we're saying instead of and instead of taking all the particles to have weight 1, we're taking them all to have like 3 soft integer weights and seeing what we get and trying to play around with that in this background. It could be interesting to look at other backgrounds as well. So, Oh yeah.
In arriving at this 3-point function, was it such that you found some expression that didn't look like a CFD correlator, and then you massaged it and pull out this extra prefactor in the CIJs? And if I then try to look at this for higher points, is the structure still the same, that you can always pull out something and you find a CFD endpoint function?
Effectively, yeah, the structure always looks like this, but the point is like these particles here, these gluons will transform as operators of weight delta and spin 1. This 3-point, what looks like this 3-point correlator here is looks like a correlation function of 3 scalars of spin 0 with weight delta -1. This prefactor effectively just corrects for that. It's really grouped this way for convenience, since effectively this this factor of 1 over Z12, Z23, Z31 comes from the Park-Taylor denominator. Okay. But I think they're exactly equal to each other. I could have just rewritten that as like the familiar 3-point function. Yeah, but this is really just some prefactor that corrects for the spin, that makes sure it transforms correctly. Like the structure. Right. Okay. Yeah, I could rewrite this formula as just this prefactor times the conformal, like the structure for 3 spinning operators. It would be exactly the same as this expression, just written in a different way. Like writing in this way sort of stresses that we have like some prefactor that depends on z's and then this sort of scalar Witten diagram, but it's exactly the same. Well, I mean, in some sense, like, or at least when we take the weights all to 1, in some sense, we're just effectively that's just setting this, to be a constant, and then and that's sort of pulling out this prefactor here. And so that might be something that is something we're considering doing, although we're also working on generalizing that to, say, the subleading soft algebra. But here again, this is just really for a convenience. I could have rewritten it. Like, I would say that at the 4-point structure, the structure would still be the same. We'd end up with a D function, the scalar contact Witten diagram at 4 points that would describe some correlator with the wrong weights and spins. And we would again get this prefactor that would make sure it transformed as or with the correct weights and spins. Sorry, so are you saying if I was like looking at the scattering of 3 scalars in this background? Okay, right, effectively what we see then, right, we'd be effectively looking at our amplitude would just be like the momentum conserving delta function. Yeah, with the background, yeah, so we'd have like, so what we'd see here is that we wouldn't have this kinematic prefactor. And then what we also wouldn't have the shifts in the weight here, right? So we wouldn't have this prefactor, and then we also wouldn't shift the weight down here by 1. Yeah, but like we would just have effectively then this prefactor would just be 1, and we would get the scalar Witten diagram times a function of beta. Mhm.
General comment, which is that, so a lot of students decide that, Natalie, so far, every statement for all of the we calculate something on the south side and it matches with something else on the bond itself, rather than this kind of statement that maybe that is maybe a bit but it's good. We can print that in theory, complete theory, and it's still this theory. So what we did was we started out with this too long and that's okay. And we computed a few things. The current, the leading current, some of it is out of level. That was just better. But I think one place where we like to go at this theory is simple enough that it might be that there might be a complete theory of the thing proposed. There might be it might be a closed theory as opposed to the opposite side. It's obviously closed to the opposite side. It would probably be more. But people like you all well, I don't think there's any difference between I think so if you have there is a very widely believed to exist, and I don't think it's that everybody has a pretty correlated. It is a similar procedure, but it's actually like one of the things. But storage is like the diamond, one of those allocated to the next sort of time and but of course, these theories don't theories don't really exist. And what we're doing is
Any more questions? Okay. If not, let's thank Walker again.